Hello everybody, Math Hobo here, and today we are going to be talking about the cousin of the parallel axis theorem, which is the perpendicular axis theorem. Now this theorem is not very well known, and it's unfortunate because the proof is much simpler than that of the parallel axis theorem. Let's dive right in. So the perpendicular. Perpendicular axis theorem says that if we have a system, if we have a rigid body, and we present this rigid body with three orthogonal axes. So let's take the x-axis, the y-axis, and the z-axis. And let's embed this rigid body in this three-dimensional coordinate plane. Then the z moment of inertia is equal to the x moment of inertia plus the y moment of inertia, and vice versa. So what we can do is we can begin by drawing a similar picture and writing out the moments of inertia for each around each axis. So we will be defining what Ix is, what Iy is, and what Iz is. And then we will be showing that Iz is simply Ix plus Iy. Now what we must do is create our three-dimensional plane, three-dimensional space. And for simplicity at least, let's use a rigid body that is embedded inside of the xy plane. So it's coplanar with the xy plane. So it doesn't lift off that plane or have positive or negative z values. The z values will always be 0. So let's consider what is the moment of inertia about x, and to do so we must identify a dm element. So an infinitesimal mass element, which is located on or inside of our rigid body. And let's ask ourselves, what is this being rotated about? So we have this rigid body, and we have the x-axis, which is like a rod going through it, and what we're doing is we're turning that rod, and we're watching this rigid body rotate around that rod. So this dm mass element here would go in circular motion about that rod, and it would maintain a constant radius with that rod. So, well, what would the radius be should be the question, and the radius is simply how much the mass element deviates from the x-axis. So that would be let's just call that deviation rx, because we're talking about the x-axis. Usually it would be ry because it's parallel to the y-axis, but that's okay. Let's call it rx for now. So then we have, due to the moment of inertia formula, we have I sub x is equal to the integral of rx squared dm. And now let's define what the moment of inertia is for rotations around the y-axis. So we have our three axes again, and this time we're going to be rotating about y. So let's introduce our same rigid body, which is coplanar with the xy plane. And let's imagine this. We have a rod, which is the y-axis, and we're spinning that rod, and the rigid body rotates around that rod. And let's identify a mass element dm here, just as we did in the previous exercise. And let's also identify the perpendicular radius, or the shortest path, the shortest line that can be drawn between dm and the y-axis. And that would be a line which is parallel to the x-axis. And let's call this length ry. So then, given these two, we have the moment of inertia about y is equal to Iy is equal to integral ry squared dm. And so rotations about z would be slightly different. Let's redraw our rigid body here. Wonderful. So rotations about z. Let's imagine this again as we did the other two. We have a rod which is the z-axis, and we're turning that rod. And since the rigid body is coplanar with the xy axis, xy plane, it doesn't really lift off z. It stays in a single plane as it rotates. And we can determine, given some mass element dn, the radius for which will be constant as it rotates around the z-axis, and that is given by the shortest, given by the line, the distance between dm and the origin. So so that distance will simply be the sum of the square, the root of the sum of the squares of the x and y components, and that's a mouthful. So let's unpack that a little here. So what we have is we want to find the distance from 0, 0, 0 to our dn. And how we do this is we have our y distance from dm, which is this. So we have ry, and we have our x. And due to the Pythagorean theorem, since iy and rx are perpendicular, we have that rx squared plus ry squared should be equal to rz squared. So let's write this out. And then rz can be written as the square root of these two. So then what we do when we plug it into the, when we plug this definition of rz into our moment of inertia, we have integral rz squared dm is the moment of inertia about z. And then what do we have? We have, let's expand rz squared. We have iz is equal to the integral of ry squared plus rx squared into dm. And we can distribute the dm and separate the integrals, because the integral of a sum is the same as the sum of integrals. So then we have I about z is equal to the integral rx squared dm plus integral ry squared dm. And well, what are each of these? Well, rx squared dm integral is equal to ix, and integral ry squared dm is equal to iy, which are the respective moments of inertia about the x and y axes. So then we have our final solution. We have iz is equal to ix plus iy. And this concludes our section on the perpendicular axis theorem. Thank you very much.